Hi, I'm continuing with the lab by talking about how we apply our spatial filters and construct our beam expander. So as you see over here, this is a microscope objective 20x, and this is a pinhole 25 micron. And we actually, before we put 25 micron in, we did try with 100 micron to get the sense of it, and we aligned the pinhole. And as you see right here, the beam come out really nice and clean because every noise is filtered out. And if the beam exactly 99% go through, all the noise wave filters and no diffraction can be seen easily. So the way that we align the spatial pinhole is basically we bring the objective far away and we align it into that we see loop, and then we bring it closer, align it again, and then continue doing that until we see no diffraction. And then we insert the 300 millimeters achromat inside with the flat side fin this side and the curved side fin the other side. And to make sure that the beam expander is highly collimated, we insert the shear plate right here. And you see all the shears fringe is horizontal to the reference line, and that is show that it's high collimated. If we move the lens inside a little bit, it's actually tilt. So that is the side that for us to see it's not collimated or not. Okay, so now I'm going to talk about sensitivity of shear plate. In this lab, we put the lens in the X, Y, and Z's to see the sensitivities by defocus it a little bit. So it can tilt one fringe and decenter defocus a little bit, one center in the other side. And we found out that with the bigger beam, this one with the big shear plate is more sensitive compared to the smaller one. The reason is this one is has higher coherent compared to the big one. So I'm going to discuss really fast how actually the shear plate works. So a shear plate basically consists of one wedge, really thin. I just want to draw it big. We have front reflection and back reflection from the second surface, and they coming out with different angles, as you see, but they both plane wave. If assume that the plane coming in is plane wave, and they go to interferes. You see the node that I draw right here, so the screen we're going to see is the interference pattern. So the wavefront can be measured as the shears, displacement, time, the distance of the fringe, and divided by the side of theta, where the theta is the angle between fringes and the reference line. So if R is infinity, means plane wave coming in, psi supposed to be 0, means theta supposed to be 0. That's explained why the fringe is horizontal compared to the reference line. So the reasons of the small shear plates is less than sensitive because it has smaller apertures plus a thinner. It's increased its coherent properties compared to the bigger shear plates, which have bigger apertures and bigger wedge, which reduce its coherent length. Coherent properties, because it's getting bigger into coherent length pictures.
For part E, we were told to measure the power transmitted through the spatial filter. So ideally, we'd like to see 99% of the initial light transmitted through. And in our case, we got 96%. So that means we were able to get a pretty clean beam through the spatial filter. Alright, so for part F, we were told to place the 200 millimeter focal length lens from last week back in the system, and the main purpose of that was just to take the collimated beam that we have and focus it down to a point. And we've had a knife edge. We placed that before and after the focal point which you can see right about here. So we place the knife edge before and after, and then profile the beam at both locations. Pause. After profiling the beam at both locations, we were able to plot the data, and just like last week, so you can see we have some sort of semblance of a Gaussian curve here, and from this we will be able to determine the beam diameter at both locations, both before and after focus.